Hello, good evening. I'm Bhavani Thuraisingam from the University of Texas at Dallas, and I'm recording this placeholder presentation, and it's going to be given actually tomorrow morning, which is November 23rd at 8:30 a.m. Dallas, Texas time, which will be 2:30 p.m. GMT, Greenwich Mean Time. Today actually is November 2nd, and it's around 9:30 p.m. Dallas time. So I'm giving this presentation as a distinguished presentation at the Imam Abdulrahman bin Faisal University in the Kingdom of Saudi Arabia. And also it's part of the Saudi Aramco chair program. And I'm very honored to give this presentation. And so I would like to share my screen now. Okay, so the title of my presentation, Integrating Machine Learning and Cybersecurity with Applications in Internet of Transportation and Infrastructures. And as I said, it's going to be given on November 23rd, 2021. And I usually record these placeholder presentations just in case there is a technology glitch. So there's always this backup presentation. But I will be live tomorrow morning to give this presentation live and answer the questions. The presentation will take around 40-45 minutes, and then we'll have around 10-15 minutes or even longer to answer questions. Okay, so my talk, it's going to be in 3 parts. Part 1 is integrating cybersecurity and machine learning. So I'm using the words artificial intelligence, machine learning, and data science sort of interchangeably. Okay, and I call this SecAI, security and AI. So in particular, I'll talk about big data security and privacy, privacy-aware quantified self, data science, ML, AI for cybersecurity applications. And then what happens if these machine learning techniques are attacked, right? So that's going to be a big problem. So I'll talk about that. And then I will discuss trustworthy machine learning AI. So these last 2 topics are one of the most, sort of 2 of the most popular topics now in cybersecurity. Okay, part 2 is completely different. I'm going to talk about security and privacy for Internet of Things, in particular, Internet of Transportation and infrastructures. And part 3 is essentially applying part 1 to part 2. So applications of security and AI for Internet of Transportation and infrastructures. A number of sponsors funded this work: NSF, Army, Air Force, NASA, NIST, NSA, and my colleagues, in particular, Professors Alvaro Cardenas, Murad Kantajalu, Latifa Khan, and our former PhD student, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, the part 1, integrating cybersecurity and artificial intelligence, machine learning, data science. Okay, so I want to give you a bit of a motivation. So data mining, right? So before data science, we had data mining, which sort of evolved into data science. So I usually use the words data mining, data science, and as well as machine learning more or less interchangeably. So I want to give some motivation about data mining, security, and privacy. So I believe I introduced the idea back in 1996. It was first mentioned at the IFIP 11.3 Data and Application Security Conference in Como, Italy. I gave a keynote address where I talked about data mining, security, and privacy. Right, and later I gave a similar presentation at the Pacific Asia Knowledge Discovery and Database Conference in 1998 in Melbourne, Australia. So I talked about how data mining could be used for cybersecurity, but yet there are very serious privacy concerns. So I published I call it a landmark paper, because I was a program director at National Science Foundation. And so I published this paper in 2002. And so when you are a program director or a program manager and you publish a paper, a sort of a high level paper, everyone pays attention, right? Because, you know, you are sort of in charge of funding. Okay, so then IBM Almaden Research Center, Rakesh Agrawal, he came up with this whole idea of privacy preserving data mining. So the whole idea, I just want to make sure that we are, just a second, right? I just want to make sure that, right, sorry, I'm not in mute. So once, I'll tell you why, because once I gave a presentation and then I was on mute and then I had to redo the entire presentation. Okay, so what he did, Rakesh Agrawal, took the original data and added noise, right? So if your age is like 26, then you want to add like 1 or 2 ages, 1 or 2 years to make it 28. And then you add noise, so it becomes X prime. And then with the modified data, you carry out the data mining and process or data science or machine learning. And then you have the final modified result shouldn't really vary because the end result should be the same. Otherwise, what's the point in doing, you know, data mining and machine learning, right? So when I joined UT Dallas in 2004, October, I had a research student, Dr. Lee Liu, together with my colleague, Dr. Murad Kantajulu. We supervised her, our first PhD student actually, between 2005 and 2008. And she came up with some alternatives, privacy preserving decision tree, and also studied how to perturb the data. Okay, so because we now have big data, right? Data mining, security, and privacy is exacerbated because of big data and data science, because lots of data are being collected and put together. So, and analyze the data so you can have huge problems, right? Privacy could be violated. So in 2014, September, I hosted a National Science Foundation workshop on big data security and privacy and presented the results at the Interagency Working Group in Washington, DC in February 2015, and quite a few efforts were funded based on this research. Okay, so at this workshop, we said lots of data being collected. So it's possible because of technological advances, you can capture, process, analyze large amounts of data for a variety of tasks. It could be for healthcare, for finance, including for security. Such tasks include user authentication, access control, anomaly detection. So you can apply data science for anomaly detection and authentication and so on. By analyzing and integrating large amounts of data collected on the web, and what you can do, it's very, very useful for disease outbreaks, homeland protection, and so on. But the problem is this data that you collect, right? Even if you anonymize the data, you can put multiple records together and you can infer, right, the private information. So, for example, when you do security tasks like authentication and biometrics and so on, you need to have voice, you can collect fingerprints, voice, and so on. But all of that, imagine for multi-factor authentication, if that data is given out, it could be disaster. So this information, if misused or stolen, can lead to privacy breaches. So at that workshop, we came up with securing the data, access control models, privacy enhanced techniques, big data analytics, and of course, secure machine learning. How do you secure the machine learning techniques? So in my talk today, the first part, I will talk just 3: privacy enhanced techniques, big data for cybersecurity, so data science, machine learning for cybersecurity, and how do you secure the machine learning techniques? I will not be discussing access control models for this particular talk. Okay, so we came up with, so we looked at quantified self-movement. Okay, so we are carrying all these mobile devices and smartphones and so on, billions of users, and sociologists and psychologists have come up with the quantified self-movement. So what they are saying, looking at the Fitbits and the glucose monitoring, blood pressure monitoring, all of the data to give us advice, right, to have better health. Like for instance, I really like milk chocolates and vanilla ice cream. And so when I go to the refrigerator and try to eat, say milk chocolates, which of course I don't keep it in the refrigerator because it's far too tempting for me. So if my smartphone says, or the refrigerator says, no, you cannot, it's not good for you, right? That will be really great. But imagine that information collected. And if somebody sends it to my insurance company, or my employer, that's not going to be good for me, right? So data collection sharing often being carried out without the user's knowledge, right? That could bring grave danger to the personal data for the user, right? Violating the privacy. For example, when you collect data from a device that monitors blood glucose levels, right? If the insurance company gets hold of it, they could not only deny coverage for me, but also for my son and for my grandchildren. So such privacy violations could easily get out of control if data collectors could aggregate financial and health-related data with tweets, Facebook activity, and purchase patterns. This could result in lawsuits against data collectors, psychological and physical distress, and so on. So what we did to address these challenges, we are saying we need tools to bring privacy into this quantified self movement. Okay, so what did we do? We came up with the policy-based privacy-aware quantified self. So you have the health, fitness data, location, social media, image, video, everything is being collected in our smartphones. And some of the data is being stored in the cloud, encrypted, and some cloud is, through cloud-based services, you can get access to the data. And what we are saying, this is what we call the privacy-aware quantified self-manager running on our mobile device. What we are saying, every step of the way, policies have to govern. So policies have to govern data collection, data storage, data analytics, data sharing. Okay, so for instance, policy-aware data collection, storage, access, analytics, learning, and sharing. So lots of data being collected, right? Some of the data could be stored in the clouds, encrypted possibly, and some on our smartphones. Based on access control policies, some local apps running on our device will be given access to some of the data. When needed, these apps can, access the cloud, via some query interface through encrypted data storage and processing. So this is really our quantified self, our cell phone, and this is the cloud. In some cases, data may not be needed, right? Fine-grained access control may not be needed. So for instance, a 20-year-old person's weight, right? You don't have to weigh that person every day, because even if that person, say, gains 5 pounds in a day, that's not going to be so much of a problem. But if a 70-year-old gains 5 pounds in a day, that could be taxing to the heart, and it could be quite dangerous. So in other cases, data may have to be deleted to preserve privacy. Example, delete and/or generate fake location data to hide the fact that persons participated in a protest. So what we are doing, we envision that data sharing and analytics will be carried out using shared services. And again, based on the different scenarios, some data could be encrypted, some could be sanitized, some could be perturbed. And so that's really the challenge. And another major challenge here is we've got to come up with appropriate policies. Now, we are computer scientists, right? So computer scientists, right, we develop algorithms and develop systems. So we come up with TOY policies. And I've been working in policies for the last, say, I got into cybersecurity in 1985 when I was at Honeywell, so for 36 years. But people often tell me, okay, your policies are very simple, right? So we are now working with the actual policy expert, our dean in our School of Economics, Policy, and Political Sciences. She's an expert in public policy. So we work with her to develop more realistic policies. Okay, so that's the privacy part. So now with respect to data science for cybersecurity, this is with my colleague, Professor Latifa Khan. So he uses past data. These 3 steps have been around for a long time. We use past data to build classification models. We predict the labels of future instances using the model and help in the decision making, right? So you could ask the question, so what is the big challenge? We've been doing this for 20, 25 years. The challenge is big data stream, massive amounts of data. Streaming data means it's continuously arriving, continuous flow of data, very common in our connected digital world, have massive amounts of data. So it's continuous, like network traffic, financial data, it's coming through the firewall. And then our classification model, we don't build one model. That is the challenge. These models are changing. Why? Because the concepts are changing. Today, it could say buy Microsoft, tomorrow buy Facebook, next day buy stocks in Apple or Amazon or Google or IBM, whatever. So the concepts are changing, so the models are changing. So we build an ensemble of models, and I'll show you in the next chart. And then the benign traffic right goes to a server when the testing data comes. So, okay, we use training data to build these models. When the test data arrives, if it's attacked, then we quarantine. Now, the challenge is to develop this ensemble of models. And so we throw away the bad models or outdated models and then update them, right? So it's joint work with our former PhD student and also our postdoc, Dr. Mahidi Masood. He's now a professor, I believe, in the university in Abu Dhabi. And Latifa Khan and myself, we wrote a book, and it's joint work actually with Professor J.W. a top-notch data science expert from University of Illinois, Urbana-Champaign. Okay, so this is sort of our idea. Now we are applying it to insider threat detection. Bad people can pretend to be good people inside an organization. So we know that, right? In the same way, bad processes can pretend to be good processes inside a computer system or a network. So insider threat requires the identification of rare anomalies, right? Where evolving behaviors, so behaviors are changing. People are adapting and modifying their behaviors. So we have designed and developed an ensemble-based stream mining algorithms based on supervised learning that addresses this challenge by maintaining an evolving collection of multiple models, right? Ensemble of models. So we have applied support vector machine for supervised learning, traditional support vector machine, and one-class support vector machine. We have also developed unsupervised ensemble-based learning algorithms that maintain sort of a compressed dictionary of repetitive sequences found throughout the data streams, right? We have the sequences of unbounded length. So this is, we really don't know what the patterns are, unsupervised, but looking at the data, we try to extract those nuggets. That's the unsupervised learning. In unsupervised learning, compression-based techniques are used to model the common behaviors. This results in a classifier that results in substantial increase in classification accuracy, right? Although we cannot train, it's hard to train, right? Supervised machine learning, it's easier to train, but unsupervised is giving us some better accuracy. This ensemble of classifiers allows unsupervised approach to outperform our static-based learning approaches. Okay. So I'm just briefly talking about a number of topics. So what is the architecture for insider threat detection, right? So a person here is typing away, and then we have I chunks, right? All these system calls and so on. We gather all these chunks, and we develop an ensemble of models, not just one model, collection of models, throw away the outdated models. The challenge is extracting features and selecting the features. And then our algorithms are unsupervised algorithm. And then we also have our support vector machine supervised algorithms. And so then the I chunks arrives, or I+1th chunk arrives, and we extract features and apply these models, and then we test, is it anomaly or not? So the process is more or less the same that we did many years ago. The algorithms are much more sophisticated these days, and also our research contributions collect to developing these ensemble models and throwing away the outdated models. Okay, so that's our insider threat detection. Okay, now what happens if these machine learning techniques are attacked? Remember, machine learning techniques are being applied for healthcare, for medicine, for cybersecurity, like I showed earlier in the earlier example. It's also being applied for retail, for manufacturing, for transportation, finance, you name it, it's being applied. If these machine learning techniques are attacked, right, instead of telling you you've got COVID, it can just tell you, oh, you've got some flu or something, right? So that could be dangerous, right? So let's look at the problem, right? So it's called adversarial machine learning. Adversary is trying to learn what we are doing, right? Adversary is trying to learn our models, our data, and it's trying to thwart us. So adversary modifies data to defeat our learning algorithms. So we've got to understand what the adversary is up to. It's not about concept drifts, that concept's changing. No, it's not online learning. Adversary is adapting to avoid being detected. It could be during training time, data poisoning, test time, modifying features when data mining is deployed. So essentially, it becomes a game playing between us and the adversary. So here, look at this, right? So this is the support vector machine boundary. You have the red squares, which are the bad instances, and the blue circles are good instances. See what the adversary is doing. It's learning what we are doing, right? Our models and our data, and then it's trying to push the red squares below the boundary so they won't be caught. So 1, 2, 3, 4, 5 of these instances are bad instances. They are insiders doing malicious stuff maybe, but they are not caught. Okay, so that is the challenge. So we've got to be several steps ahead of the adversary. Okay, so before we talk about the solution, we have to study what types of attacks. An example, adversarial attacks. So we have looked at different types of attack models. In particular, in our paper at the Knowledge Discovery in Database Conference, we've got 2 types of attacks, the free range attack and the targeted attack. So free range attack, adversary moves the malicious data, right? In a particular, anywhere in the domain. So there's a lower bound and upper bound anywhere. So for every J in 1D, so all of this is in our paper, and I'll give you a reference to our paper. And so that's the free range. And the targeted attack, adversary can move malicious data closer to the target point. Okay, so we need to study these types of attacks, and based on these attacks, we have come up with a solution. So adversarial support vector machine. What does that mean, right? So this used to be the original boundary. These dotted lines, black dashed line is a standard support vector machine boundary. And what we are trying to do, so the green circles are the good instances, the red crosses are the bad instances. And so anything beyond this line, these red crosses are bad instances, but they're showing up as good instances. So what we are trying to do is study the patterns. It's not very straightforward, a lot of mathematical game theory approach. And so we are trying to move these dashed line to an appropriate position. So we are moving this here. By moving it to the blue line, right, all of these red instances are now showing up as, okay, so by moving these, so by moving this dash line, okay, here, so we are sort of solving the problem, right? Because when it was here, below this line, everything was bad. But these bad things were being shown as good stuff. But by moving, these red crosses are being shown as bad, right? And so this is really better explained here, where you have the bad instances and the good instances, and the black crosses are the bad instances, and a lot of the crosses are being, we are finding them because we have moved the line. So essentially, test time, deployment time attacks, the attacker can, what can the attacker do? Can modify the data X to X prime, modify the packet length, can add dummy bytes, good word to spam email, noise to an image. So you could ask the question, why can't we move this blue line right here? Then all the bad instances would be caught. But imagine if we move the blue line here, the green circles, which are good instances, will show up as bad instances. We don't want false positives and we don't want false negatives, right? So that's the challenge. So, and our paper is, this was one of the early papers in 2012 with my colleague, Professor Murad Kantajulu, and Yan Zhao, who is our research scientist. So this was really got a lot of visibility because it was one of the early papers in adversarial machine learning. As I said, it's one of the hottest topics. Okay, so what's happening now? The whole area of trustworthy machine learning, because what happens here, machine learning is being attacked, right? So one solution is trying to develop these game theoretic solutions and move this line to the blue line. Another solution is, what we are saying is, computations over big data require massive computation resources. Third-party survey is used for computation. Data inherently becomes available in untrusted environments, like man-in-the-middle attacks during data transmission and so on, insider threat from adversaries. So we can do some of the machine learning, right, execution can be carried out in hardware. So Intel has come up with secure encrypted stream data processing, the SGX chips, right, platform. So that's the trusted execution environment. And so we can execute some of the trusted code in the Intel SGX platform. And I'll show you in the next chart. So that's one approach. And then the other approach, I was in a panel about a year ago, and there was this professor, a lady from University of Oxford in the UK. She talked about formal methods for machine learning. And I've been following up on that more recently and wrote sort of a 2-page sort of brief write-up on that. Applying formal methods for machine learning, including logics for specification for deep learning and the verification of machine learning algorithms. That's also very promising. I know formal methods have been around for a long time, but more recently they are becoming, I mean, they've been applied for hardware verification and so on, but now with more sophisticated methods, because we want to come up with formally verified machine learning algorithms so we know that the code, the software that we have implemented meets the specifications. Okay, so the Intel SGX platform, very briefly, right? So you have the application memory, SGX runtime library, and encrypted code, and the algorithms, the data analytics algorithms are being executed in this SGX enclave memory in secure locations. And that way you can protect these machine learning algorithms. Okay, that's the whole idea. Okay, so now we finish part 1. Now we move into part 2, which is security and privacy for Internet of Transportation and critical infrastructures. What is Internet of Things, right? So you can see our coffee maker is connected to our television, to our alarm clock, to our, our wireless mobile devices, to our Amazon purchases, to our smartphones. Everything is connected. They are all connected wireless, and they are all talking to each other, lots of sensor data being communicated. Of course, imagine if any one thing is attacked, the whole thing is crashing. Even worse, in the Internet of Transportation, cars are talking to each other, cars are talking to trains, and they're talking to trucks are talking to cars, to roadworks, everybody's talking to each other. And imagine if any of these things are attacked, the whole Internet of Transportation is attacked, and then it could be devastating, all kinds of accidents and fatalities. Okay, so Internet of Transportation, Internet of Things, we know, has a major implications, right? In transportation industry, there's Internet of Medical Things, Internet of Transportation, Internet of manufacturing things, various Internet of Things. So autonomous vehicles, they are aiming to improve day-to-day activities, delivering packages, improving traffic like drones and so on, transportation of goods. In the US, trucks alone carry an estimated 63.3% of freight goods. AVs, autonomous vehicles, not just limited to ground, but also aerial, like airplanes and drones and sea vehicles, wide range of applications. Levels of automation, we've noted that they range from 0 to 5. Right, ground vehicles have a low automation level of 2, while aerial vehicles have a high automation level of 4. So companies are investing heavily in AVs. GM spent about 728 million in 2018, 1 billion in 2019, and I'm sure it's more in 2020. I've got to get their 2020 numbers. While there's a lot of potential in AVs and the improvements, it can do lots of good things to the transportation industry. Of course, security and privacy, it's a major concern. It can pose new challenges that have to be addressed as we move forward. Okay, security of autonomous vehicles. So that means we have to ensure that these autonomous vehicles are secure. They could be attacked. AVs emulate their environment using a variety of sensors, right? We know the camera, GPS, inertial measurement units, LiDAR, radar, ultrasonic sensors. So prior research has shown that sensors are susceptible to malicious tampering, such as IMUs, the inertial measurement units, are susceptible to sound waves, and GPS, global positioning systems, receptors are susceptible to spoofing signals. Vehicles should verify the veracity of sensor signals before acting upon them. Right? So the autonomous vehicles rely on sensors to evaluate and interact with their environment. That's sensor-based. So let's look at what happens. Inherited issues, of course, sensors are susceptible, as we said, to GPS spoofing, transduction attacks, and manipulate the environment like virtual sound, magnet, and so on, and needed defenses. We need defenses. But what we have, classical computing security, like we look at memory protection, cryptography, authentication, and so on, right? They do not protect against some of these specific attacks. So we need to come up with some new solutions. And then no verification, it's all real time, right? So due to the real-time constraints, AVs trust and act upon sensor data without any form of verification. So essentially what we are saying is current verification methods are not sufficient. Okay, so what did we do? So initially we didn't look at AI or anything like that, machine learning. We just looked at developing a physics-based, right, reference monitor. Reference monitor is that part of the security kernel that has to be secure. It's enforcing all of the security properties, right? So we developed a model that is physics-based, anomaly detection algorithm for ground and aerial vehicles. So we have a three-part algorithm. We build a model offline of the AV's physical invariants, implement an online tool to monitor expected and observed behavior to detect anomalies, raise an alarm if significant residual difference exists between executions. So offline pre-processing, online verification, and anomaly detection. Okay, so we published this paper in Usenext, and we have another paper that just got the best paper award last week at the ACM CCS Cyberphysical Systems workshop. Okay, so you could say, okay, so what's the big deal? Offline processing, online verification, anomaly detection. This is what has been going on for such a long time. Well, it's in the physics because we've got to model the entire cyber-physical system, right? So I'm not a control system person. So my colleague, Dr. Cardenas, is a brilliant control systems scientist as well as a cybersecurity specialist. So he's in cyber-physical system. So he takes the physical system and then he models it, right? So you have parameters like the case, input sensor measurements, pre-processing sensor reading, command to rotors, predictor states, XYZ axis moments of inertia, and emis mass and drag factor and so on. So first thing is offline pre-processing. What does it mean? You got to take the autonomous vehicles invariants, calculate using a well-known nonlinear model. We only did for aerial, air, and ground, drones and cars. Okay, so for accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z or Z axis is used for the aerial vehicle. Vehicle position and steering is used for the ground vehicle. So this is the model. Then the online processing, we didn't use machine learning, an extended Kalman filter. Kalman filters have been around for a very long time. It's used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. The algorithm is divided into two sections, predicts and corrects the estimation before it is compared against the sensor data. Okay, so that's the online stage. And then the anomaly detection, we use the CUSUM, C-U-S-U-M. That's a statistical based algorithm is used to detect persistent attacks. And you raise an alarm if the residual difference is larger than a predefined threshold. Okay, so the approach is, is sort of pretty much standard, but the challenge again is to model the system and develop algorithms for that particular system. Okay, so our implementation, we did aerial vehicle and ground vehicle. So aerial vehicle, Intel ready to fly drone controller. So this is aerial, PX4 controllers focused on detecting GPS spoofing and gyroscope attacks. GPS detected in 0.2 seconds, gyroscope detected in attacks 1.5 seconds. Overhead is around 5.4%. For the ground, we used AVs. We used custom build on top of Traxxas Ford Fiesta. Controller is ROS Kineticam, focused on detecting visual attacks on the camera, attacks detected after 0.1 second. Overhead introduced is 2.25. Each threshold produces a probability of false alarms of approximately 2%, which is quite high actually, right? Because we want the false alarms to be very, 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 very tiny, small. Okay, so that's our security part. Privacy, we really haven't done as much but it's really crucial, right? Because beyond the security of individual vehicles, the transportation sector could greatly benefit from supporting infrastructures, right? Communication between vehicles, motion centers. So we really need this communication because you can reroute the vehicles into different paths. maybe warn them if there is traffic jams or there's going to be danger. So from the user's perspective, right, all of these algorithms are helping, right, the transportation ecosystem. But from the user's perspective, privacy could be violated. For instance, right, if a user is smoking inside the car or user is in a particular location that he or she does not want to be known, right, it could lead to private information being exposed, vehicle identification, driving patterns. I wouldn't want my driving patterns to be photographed and sent to my insurance company, right? So legislators, engineers, and scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving public perception, reduce hesitation from consumers, and this way, if you know there's some level of privacy, right, consumers will be willing to adopt sort of new technologies. So again, without a doubt, Internet of Transportation, all of this communication between sensors is going to help us a lot, but they could be attacks, so a security problem. But with all this communication, privacy of the individuals could be violated. So we need to keep privacy in mind. Okay, so that finishes part 2. So now I have a few charts that's going to talk about, that's part 3. How can we apply part 1 to part 2, which is applications of security and AI for Internet of Transportation and infrastructures. Okay, so data science AI for transportation security, right? So remember, we talked about 3 things. One is data science for cybersecurity. Number 2, what happens if the data science or machine learning techniques are attacked? And number 3, privacy. So first, data science for transport, AI, ML for transportation security. Internet of Transportation System subject to attacks, right? And we applied Kalman filter and so on. But it's streaming data. Remember, sensor data is continuously arriving, so it's streaming. Our Kalman filter, we never developed an ensemble of models. It was just a one-time thing. That's the challenge. This data is coming in from all directions, and it's also the concepts are changing. It could be danger one time, no danger another time. So as transportation systems go electric, the streaming data being collected in the future is going to be driverless when they go electric, energy conservation. So threats to security means you could, massive damage, including loss of lives, accidents. You could, get stranded in lonely highways. So data science ML techniques are being applied. So without a doubt, there is this urgent need to apply machine learning. We may need to come up with an ensemble of models that I mentioned earlier for our inside the threat detection work. The question I have, and that's our research is just beginning here, can stream analytics learning techniques that we applied, say, to financial data, network data, telecom data, can they be applied to transportation data? I believe we can. And we have to come up with this ensemble of models, and they have to function in real time. The main question is to understand the nature of the complex transportation data and adapt the stream analytics and apply them on the massive amounts of heterogeneous sensor data being collected. Okay, that's one point. The next, I talked about adversarial machine learning. What happens if these machine learning techniques are attacked? Without a doubt, the Internet of Transportation System, there's going to be machine learning, right? Machine learning is going to help these transportation systems to avoid collisions, avoid accidents, the best routes to follow, so much of advice. Autonomous vehicles depend on AI, right? Optimum directions, driving without a human in the loop. So many advantages using machine learning. However, the adversary is watching our data, watching our models, and it's trying to thwart our models. Imagine if these machine learning techniques are attacked, there could be utter chaos, right, in the transportation industry. So adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt. We've got, just like we moved the support vector machine, the blue line, it has to adapt to thwart the adversary's actions. Eventually, it becomes game playing between the adversary and the vehicle's machine learning algorithms, right? So what's the challenge? What sort of game are we going to play? Is it zero-sum game, Bayesian game? We need to understand the data. That is essential. And research on this topic is only just beginning, right? So a lot of work to be done here. And remember, privacy-aware, policy-based data management framework for our cell phone, remember? Now we want to apply it for the quantified self. but we want to now apply it for transportation systems. Instead of cell phone, we have a car. Inside the car, there's some kind of a gadget, which is collecting data, storing data, accessing data, analytics, and sharing. Some data could be in the cloud and through cloud-based services, but the data is not social media and radar GPS, it's social media, healthcare, and so on. Instead, it's radar, GPS, cameras, LIDAR, ultrasonic sensors. Now, we haven't started research in this area, but I think in the future, we'll have no choice but to expand on this, right? So that's something we are planning for the future. And what we are saying is policies have to govern. Policies have to say what data to collect, what data to store and access, what data to analyze, how do we analyze, how do we share. So that's for the future. So now I come to my last chart, right? Developments in integrating cybersecurity and AI, they are exploding, right? And that's right, one of the hottest topics now in cybersecurity. Applications of AI for security, like insider threat detection, malware analysis, security for AI, adversarial machine learning. Also developments in privacy-aware healthcare and managing one's life's activities. That's the privacy-aware quantified self. So that's what a lot of our research has been focusing on. But now we have the Internet of Things, in particular, Internet of Transportation and Infrastructure. So security and privacy solutions are being developed mainly physics-based solutions. So as driverless cars become a reality, more and more of the AVs will use AI ML techniques, right? So the question is, how can we develop AI solutions for detecting malware in AV systems, right? So how can we develop this machine learning for detecting malware in autonomous vehicles? And what happens if these machine learning techniques are attacked? So how can we bring in all this adversarial machine learning work into this autonomous vehicle systems? So that's really an urgent challenge for us to investigate. And so we are focused on the first part, but we haven't really started our research on the second part. So first part is what we are focusing on, right? How can we apply machine learning for detecting cyber attacks in autonomous systems, autonomous vehicles? Second, can we develop a privacy-aware policy-based data management framework, just like we did for quantified self? Can we develop that for Internet of Transportation and infrastructures, right? So that's the example with the car. And then remember I talked about trustworthy machine learning using Intel chips or the Intel platform, and then the formal methods for security, for machine learning. Can we bring in formal methods for the machine learning for IoT security? And can we bring some of the trustworthy machine learning techniques, right? So how can we bring an Intel execution platform into this environment? So that's really the question, right? So numerous opportunities for substantial research and development. Okay, so whatever I've mentioned, I know it's a high level, but I've covered three major topics, right? Integrating cybersecurity and AI or machine learning. Number two is Internet of Transportation and infrastructures in general, security and privacy. Number three, how can we apply security and machine learning techniques? How can we integrate it for security and privacy for transportation systems? That's really the future. And I would like to thank all my colleagues. Professor Alvaro Cardenas is a top expert in cyber-physical system security. He was with us, but he has joined University of California, Santa Cruz. Dr. Murad Kantajulu, he's a top expert in adversarial machine learning. Professor Latifa Khan, he's an expert in data science for machine learning. By the way, Professor Latifa Khan is also very interested in giving talks to the Imam Abdulrahman bin Faisal University, to your program, the Saudi Aramco chair program. So he's very interested. He's really a top expert in data science, machine learning, and also a lot of experience in applying it for cybersecurity. And our former PhD student, Dr. Raul Quinones, he's working for a company now, continuing in this direction, in this work. And of course, Ms. Rhonda Walls, she's our project coordinator. And so she really supports us, in lots of our activities, right? So I'm going to stop sharing. And again, this has taken, yes, it has taken about 18 plus 30, around 45 minutes, right? So my talk will be 45 minutes and I'll be there for about 20-25 minutes. I'll be there to answer. They said 15 minutes questions, but 15 to 25 minutes I'll be there in the morning to answer the questions, right? So in case there is a technology glitch, hopefully they'll be able to play this presentation. I hope not, right? But once, only once it happened to me, actually. I've given probably around 27, 28 keynote addresses and about 10, 15 different talks and about 10, 15 different panels during the pandemic since March 2020 to now. Only once, about a month ago, towards the end of my presentation, for about 5 minutes, our internet went down. But if internet goes down, if you give me 5 minutes quickly, I can bring it up. I got to just switch it off and switch it on. But otherwise, I've also I'll be giving to this seminar organizers, I'll be giving my cell phone. So please, you can call me on my cell phone just in case something happens, but hopefully everything will go well tomorrow morning. And again, thank you very much to the chair and to the administration of the Imam Abdulrahman bin Faisal University in the Kingdom of Saudi Arabia. Thank you very much, and I will see you in the morning. Thank you.